Hello there, and welcome to the Sleepy Science Channel. Tonight, we drift into one of the deepest mysteries in all of physics, light itself. It is not made of matter, yet it carries pure energy across the emptiest parts of space. It moves with a precision that never changes, no matter who observes it or how fast they are moving. Every image of a distant galaxy, every theory of relativity, every glimpse into the first moments after the Big Bang begins with light. It is both our messenger and our measure. Through it, we see how the universe behaves and how time itself unfolds. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. For now, just breathe. Let your eyes grow heavy, and like the mystery of light, cradle your thoughts. Let's begin. Light exists as both a wave and a particle. Light behaves in ways that challenge everything we think we know about nature. In some experiments, it moves like a ripple, spreading out and overlapping to form patterns that only waves can produce. Yet in others, it behaves as individual packets of energy, striking one at a time like particles. Both descriptions are correct. Light has a dual identity that depends on how it is observed. When it travels freely, it acts as a wave, carrying energy across space. When it interacts with matter, it arrives as a discrete quantum of energy called a photon. This strange duality is not unique to light, it applies to all fundamental particles. Electrons, atoms, and even molecules show the same pattern of behavior under the right conditions. The quantum world reveals that reality does not follow classical intuition. Instead, it follows probabilities, unfolding differently depending on how we choose to look. Every color is a different frequency of the same energy. The light we see as color is just one continuous phenomenon vibrating at different rates. What appears red, green, or blue to the human eye is the same energy oscillating at distinct frequencies. Red light vibrates more slowly, while violet light vibrates more quickly. These variations form what is known as the visible spectrum, a narrow band within a much broader range of electromagnetic energy. Beyond red lies infrared light, which we feel as warmth, and beyond violet lies ultraviolet, which carries enough energy to cause sunburn. Our eyes evolved to detect only this limited range because it is the region most abundant in sunlight at Earth's surface. Every glow, spark, and reflection you see is made of these same oscillations, differing only in frequency. The full electromagnetic spectrum extends far beyond what we can perceive, yet every wavelength is part of the same unbroken field of light. Sunlight takes 8 minutes to reach Earth. The sunlight that reaches us each day began its journey just over 8 minutes earlier, racing through the vacuum of space at the fastest speed nature allows. But the story of that light starts long before it escapes the sun. Deep within its core, hydrogen atoms collide and fuse to form helium, releasing vast amounts of energy. Photons born there are absorbed and re-emitted countless times as they travel outward through dense layers of gas, a process that can take hundreds of thousands of years. Once they finally reach the surface, they stream freely into space. Some of those photons cross the gulf to Earth and touch your skin as warmth. When you feel the sun on your face, you are sensing the last step of a journey that began inside a star. Energy that left the solar surface minutes ago, but was created ages before that. Starlight lets us see into the distant past. When you look up at the stars, you are not seeing them as they are now, but as they once were. Light takes time to travel, and even the nearest stars are many trillions of miles away. The glow you see began its journey years or centuries ago, carrying with it a snapshot of the universe's history. Some of the faint smudges we call galaxies began shining billions of years in the past, when the cosmos was young and still taking shape. Telescopes act as time machines, gathering that ancient light and allowing us to study events that occurred long before the Earth formed. When astronomers measure the color and brightness of starlight, they can deduce temperature, composition, and motion, revealing the evolution of stars and galaxies over cosmic time. The night sky is therefore not just a view of space, but a window into deep history. Nothing travels faster than light in a vacuum. In the universe as we know it, nothing can exceed the speed of light in empty space. This limit is not simply a measurement. It defines the structure of reality itself. Every event, every exchange of information, and every flow of energy must obey this rule. When objects move closer to that ultimate speed, time for them appears to slow relative to an outside observer, and distances in their direction of motion appear to shrink. To actually reach or surpass that speed would require infinite energy, which is impossible under known physics. The constancy of light's speed in all reference frames is what led Albert Einstein to formulate the theory of relativity, forever linking space and time into one fabric. Light is not only the fastest traveler, it sets the pace by which all other movement, cause and effect must unfold throughout the cosmos. Light can be slowed to a walking pace. In empty space, light moves at its maximum possible speed, but when it passes through a material, its progress slows. Inside glass, water, or air, photons are absorbed and re-emitted by atoms, delaying their journey. Usually this slowdown is slight, but under very special conditions it can become dramatic. In laboratories, physicists have used ultra-cold clouds of atoms to slow light to the speed of a gentle straw. They have even stopped it entirely by storing its energy and pattern within the atoms themselves, then releasing it later unchanged. This does not mean light loses its identity, but that it temporarily transfers its information into matter. These experiments demonstrate how tightly linked light and matter really are. The same principles make possible advanced technologies like optical fibers, lasers, and quantum memory systems that may one day transform how we communicate and store information. Some colors are forever invisible to the human eye. Human eyes can see only a narrow part of the electromagnetic spectrum, a range that runs from red through violet. Beyond those limits lies an invisible universe of light. Infrared radiation carries warmth, but cannot be seen. Ultraviolet carries more energy than visible light and can damage skin, yet it remains invisible to us. Other animals perceive parts of this hidden world with ease. Bees see ultraviolet markings on flowers that act as landing guides. Some snakes can detect infrared radiation from the bodies of warm-blooded prey, allowing them to hunt in total darkness. Using cameras and sensors, humans have extended vision beyond biological limits, revealing patterns and structures that were once unseen. Through these tools, we can observe the heat signature of a living creature, the glow of a distant galaxy, or the spectral fingerprints of atoms light years away. The oldest light still glows across the universe. Long ago, when the universe was still young, it was filled with a thick fog of charged particles that trapped light. As the cosmos expanded and cooled, those particles combined into neutral atoms, allowing light to travel freely for the first time. That light still fills space today as the cosmic microwave background. Though invisible to human eyes, it can be detected as faint microwaves coming from every direction. It is the oldest light we can see, a direct remnant from the time when the first atoms formed. Over billions of years, as space stretched, its wavelengths lengthened and its energy decreased. This background glow records tiny variations that reveal where matter gathered to form galaxies. By studying it, scientists learn about the age, shape, and composition of the universe. It is the earliest message we have ever received, still crossing the cosmos today. Sunsets burn red because blue light scatters away. When sunlight passes through Earth's atmosphere, it interacts with countless air molecules that scatter shorter wavelengths, such as blue and violet, far more strongly than longer ones. During the day, this scattering spreads blue light across the sky, creating its familiar color. Near evening, the sun's light travels through more air before reaching your eyes. Much of the blue and violet light is scattered out of view, leaving behind the warmer hues of red, orange, and gold. Dust and water vapor can enhance the effect, deepening the colors or spreading them across wide bands. Every sunset is shaped by local conditions, the amount of moisture, the size of particles, even the angle of the sun. What you see is not the sun changing color, but the atmosphere acting as a vast natural filter that allows only the longest wavelengths to reach you directly. Lightning creates light hotter than the surface of the sun. During a thunderstorm, the air becomes charged as currents of electricity build between clouds and the ground. When that charge becomes too great, a sudden discharge occurs, creating lightning. The current travels through the air with tremendous energy, heating the surrounding gas to tens of thousands of degrees. In that instant, the air glows as atoms are stripped of electrons and become plasma, a luminous state of matter. The brightness of a lightning flash spans nearly every color of visible light, which is why it appears white to our eyes. The rapid heating causes the air to expand explosively, producing the sharp crack of thunder. Though brief, each strike releases enormous power and triggers chemical reactions in the atmosphere that form nitrogen compounds later carried to the ground by rain. Lightning is both destructive and creative, reshaping air and soil with each brilliant flash. Some creatures see hidden worlds in ultraviolet light. Many animals perceive light that humans cannot see. Bees, butterflies, and a wide range of birds detect ultraviolet wavelengths that lie beyond the violet edge of human vision. To them, landscapes are marked with signals we miss completely. Feathers can carry ultraviolet accents used in mate choice. Fruit ripeness may stand out with greater clarity. Even rodent urine reflects in ultraviolet, leaving trails for predators to follow and for others to avoid. Human eyes filter this radiation to protect delicate tissues, which is why the world looks simpler to us. With specialized cameras and sensors, researchers reveal how ordinary scenes transform when ultraviolet is visible. Patterns leap from petals, plumage glows with hidden contrast, and surfaces that seem uniform to us become richly mapped. This broader sensory field gives these animals advantages in foraging, navigation, and communication, reminding us that our visual experience is only a narrow slice of what truly surrounds us. Flowers use ultraviolet patterns to guide bees. What appears as a single color to human eyes can hold intricate guidance systems for pollinators. Many flowers display ultraviolet patterns that act like visual runways directing bees to nectar and pollen. These markings often form radial lines, dark centers, or rings that sharpen contrast under ultraviolet light. The signals reduce search time for pollinators and, in turn, increase the chances that pollen is transferred efficiently between blossoms. This is a co-evolved conversation written in wavelengths invisible to people. When botanists photograph petals with ultraviolet sensitive equipment, familiar blooms reveal striking target shapes that are otherwise hidden. The shapes vary between species, ensuring recognition and fidelity among pollinators. Weather, soil, and plant health can subtly shift the intensity of these cues, adding another layer of information. Through this partnership, light becomes a shared language that aligns animal behavior with plant reproduction, and keeps ecosystems humming with quiet precision. Refraction bends light and creates illusions beneath water. When light crosses from air into water, it changes speed and direction. This bending, called refraction, makes a straight straw appear kinked at the surface and causes fish to seem closer than they are. Refraction enables focusing in the eye and underpins every lens in glasses, cameras, and microscopes. Different materials bend light by different amounts because their internal structures delay the wave to varying degrees. That property, known as refractive index, determines how strongly a lens will focus or spread a beam. The angle of entry also matters, which is why a shallow view across a lake warps the scene more than a view straight down. Prisms rely on refraction to peel colors apart, since each wavelength shifts by a slightly different amount. From crystal sparkle to mirages dancing on hot roads, refraction is a single principle expressing itself through countless everyday illusions. A rainbow is a full circle you rarely see in full. A rainbow is not an arch drawn on the sky, but a complete circle formed by countless droplets acting together. Ground and horizon usually block the lower portion, so the half ring is what most observers notice. Each droplet bends incoming sunlight, reflects it internally, and bends it again on the way out. The geometry fixes the apparent angle of the colored band relative to the line opposite the sun, which is why the bow keeps a constant height as you move. From aircraft or high ridges, the circle can appear whole, with the observer's shadow centered inside it. Because the display depends on the exact position of the observer, no two people ever see the same rainbow. Fog, spray, and even garden mist can produce miniature versions. A rainbow is a personal alignment between sun, droplets, and eye, an elegant proof that perspective and physics always work together. Every raindrop acts as a tiny prism. Falling raindrops perform a vast, coordinated experiment in optics. Sunlight enters each droplet, slows, and bends. A portion reflects from the back surface, then bends again as it exits. That path separates colors because each wavelength shifts by a slightly different amount. Larger droplets tend to produce sharper, more saturated bands, while smaller droplets create a softer pastel spread. Wind shear distorts drops from perfect spheres, adding subtle texture to the pattern. The arch in the sky is not a single object, but the combined contribution of uncountable droplets, each sending a narrow beam of colored light toward a particular viewpoint. Move a few steps and a different set of droplets complete the effect. The same physics paints bows in waterfall spray, surf, and fountains. What seems like a monolithic sign in the clouds is really a shimmering sum of many little prisms at work. White light holds every color at once. White light is not an absence of color, but a balanced presence of all visible hues. A prism, or thin film, reveals this by separating the blend into a continuous spectrum. The eye perceives white when the three types of cone cells are stimulated in proportions that the brain interprets as neutral. Different sources produce different whites because their spectral blends vary. Sunlight offers a remarkably even distribution, while many lamps favor warmer or cooler components. In photography and cinema, careful balancing ensures that skin tones and fabrics appear natural under changing illumination. Astronomers read stellar spectra to infer surface temperature and chemistry from subtle shifts within what might look white at a glance. Painters and designers exploit these nuances by choosing lighting that flatters color relationships. Far from being plain, white is a harmonious chord made from many notes resonating together. Crystals slow and split sunlight into spectral fans. The internal order of a crystal determines how light moves through it. In some minerals, the structure allows two distinct paths with different speeds, a property called birefringence. Hold a clear calcite fragment over text, and a double image appears because the beam divides inside the crystal. Rotate the crystal and the images dance as the orientations change. Cut gemstones sparkle because light bounces and refracts through carefully shaped facets, sending narrow beams outward at precise angles. In the atmosphere, tiny ice plates and columns can refract sunlight to create halos, arcs, and bright mock suns that frame the sky. Laboratories use engineered crystals to filter polarizations, tune wavelengths, and steer laser beams with exquisite control. Whether in jewelry, clouds, or instruments, crystals demonstrate that beauty and precision emerge from the quiet regularity of atoms repeating in space, guiding light along ordered pathways. The human eye sees only a thin slice of the spectrum. Human sight spans a modest band of wavelengths from deep red to violet. Longer wavelengths become infrared, microwaves, and radio. Shorter wavelengths continue to ultraviolet, X-rays, and gamma rays. The atmosphere and the spectrum of the sun shaped this biological window, favoring wavelengths that reach the surface and reflect richly from leaves, skin, and stone. With technology, people now explore beyond natural limits. Infrared cameras reveal heat patterns and penetrate dusty regions of space. Ultraviolet detectors highlight mineral traces and biological fluorescence. Radio arrays map cold gas between stars, while high-energy telescopes track violent events near compact objects. Each band offers a different perspective on the same universe, like multiple languages describing a single story. Human vision is a wonderful starting point, but instruments have taught us that light is far more varied and informative than our eyes alone suggest. Some creatures make their own light in the deep sea. The deep ocean is a realm without sunlight, yet it is not truly dark. Many organisms create illumination through bioluminescence, a chemical reaction that releases energy as visible glow. Anglerfish wave lures that seem to bloom from living lanterns. Jellyfish pulse soft halos that startle predators and attract mates. Shrimp eject sparkling clouds to confuse attackers. Tiny plankton flare when waves disturb them, tracing bright lines along a moving hull. The emitted color is often blue or green because those wavelengths travel far through seawater. The process is highly efficient, converting stored chemical energy into light with minimal heat. Scientists adapt these reactions as markers in genetics and medicine, where faint glows report on cellular activity. In the ocean's quiet night, light is not a luxury, but a tool for communication, camouflage, hunting, and survival, woven into nearly every level of the food web. Fireflies glow through nearly perfect cold light. Fireflies signal with flashes produced by a reaction between oxygen and a compound called luciferin inside specialized cells. An enzyme controls the timing, allowing precise pulses that serve as species-specific signatures. The light is exceptionally efficient, releasing energy mostly as visible glow rather than heat, which is why it is called cold light. Patterns vary by habitat and season, turning summer fields into gently synchronized displays. Researchers use the same chemistry to create biological reporters that glow when particular genes turn on, or when specific molecules appear in living tissue. The efficiency of the firefly's lantern has inspired designs for roughened LED surfaces that extract more light. In wetlands and forests, fireflies also act as indicators of environmental health, since their life cycles depend on clean water and stable habitats. A simple pulse from a tiny insect thus connects ecology, evolution, physics, and technology. The ocean sometimes glows with living light. Coastal waters can shimmer at night when plankton release brief flashes in response to motion. A breaking wave, a swimmer's hand, or even a boat's wake ignites a trail of blue-green sparks. The underlying chemistry is a form of bioluminescence that converts chemical energy into light with minimal heat. The flashes may deter predators by drawing attention to moving hunters, or they may serve as a startle tactic that buys time for escape. Conditions such as warm surface layers and nutrient pulses favor these blooms, though the phenomenon can appear in many climates. Photographers capture the glow by using long exposures, revealing swirling paths that the eye can only glimpse. While the spectacle feels otherworldly, it is simply physiology meeting physics in the open sea. The ocean writes calligraphy with light, and every letter is drawn by a living cell reacting to touch. Auroras paint the sky when the sun meets Earth's atmosphere. Charged particles carried by the solar wind funnel along Earth's magnetic field toward polar regions and collide with atoms high above the ground. Oxygen emits green and red photons at characteristic energies, while nitrogen produces blues and purples. The result is a moving curtain of light that follows invisible magnetic lines. Auroras intensify during active periods on the sun, when large eruptions send additional particles outward. Space weather forecasters track these streams because they can disturb satellites, radio links, and power grids. From the ground, the display looks gentle, yet it is driven by immense energies delivered from space. The forms can ripple, arc, and fold as the magnetosphere responds to gusts in the solar wind. This is not merely a pretty sky event, but a visible sign that Earth and its star are in constant electrical conversation across vast distance. Light can twist like a tornado as it moves. Light waves can carry a helical structure known as orbital angular momentum, which means the phase front spirals around the direction of travel. Special optical elements imprint this twist, creating beams with a central dark core and a corkscrew pattern. Such beams can trap and rotate microscopic particles, acting like tiny optical wrenches. They can also encode information in the amount of twist, adding channels to communication systems that already use color and polarization. Atmospheric turbulence can impart similar effects, which researchers study to improve imaging through air. In astronomy, twisted light measurements may one day help probe the rotation of distant objects. The existence of this property reminds us that even a simple beam can hide complex structure. Light is not just brightness and color. It is also geometry in motion, capable of carrying shape as well as energy from place to place. The ocean's color comes from how light scatters, not its depth. Water absorbs red and yellow wavelengths more strongly than blue, so the components that remain after modest travel are those shorter wavelengths that scatter widely. That is why clear open water often appears a deep blue, while coastal water rich in phytoplankton or sediment shifts toward green or brown. Clouds, wind, and surface roughness further modulate the appearance by changing how light enters and exits the water. Over sandy bottoms, reflected light adds pale turquoise tones. Over dark rock, the same water can look almost indigo. Satellite instruments read these subtle shifts to estimate chlorophyll levels and track ocean health. The sea's color is therefore not a simple mirror of the sky, and not a direct gauge of depth. It is a living signal of absorption and scattering that broadcasts what lies within, written in shades that change with season, weather, and life. The sky appears blue because shorter wavelengths scatter more. Air molecules are tiny compared with the wavelength of visible light. When sunlight meets them, the interaction favors the shorter wavelengths, which scatter broadly across the sky. Human eyes are more sensitive to blue than to violet, so the overall impression is a blue dome overhead. Near the horizon, where light travels through more air, the scattered path favors paler tints. At sunrise and sunset, the direct beam loses most of its short wavelength content, letting warmer colors dominate the path to the eye. The same scattering softens distant mountains and gives them a bluish haze, since multiple scatterings favor the short end of the spectrum. This is not pigment in the air, but geometry and scale at work, a quiet process that runs without interruption and paints the atmosphere anew each day. The moon shines with reflected sunlight. The moon has no glow of its own. Its surface scatters sunlight in all directions, acting like a rough mirror made of dust and rock. Only a modest fraction of incoming light returns to space, yet against the dark sky that reflection feels bright. The changing phases are simply varying views of the sunlit half as the moon orbits Earth. Craters and mountains cast long shadows near the terminator line, carving relief that even small telescopes can reveal. Subtle color differences trace variations in mineral content across volcanic plains and highlands. During a total lunar eclipse, sunlight refracted through Earth's atmosphere bathes the surface in a copper tone, a global sunset projected onto another world. For navigation, ritual, and science, this borrowed light has guided human attention for millennia, transforming a silent rock into a nightly companion. Sunlight powers every living thing on Earth. Photosynthetic organisms capture sunlight and convert it into chemical energy that feeds food webs on land and in the sea. Plants channel this energy into sugars and structural materials. Herbivores eat the plants. Predators eat the herbivores. Decomposers return nutrients to the soil, readying the cycle for another turn. Sunlight also drives evaporation and winds, shaping weather and climate. Even fossil fuels are ancient sunlight stored by organisms that lived long ago. Biological clocks synchronize to daily light cycles, regulating sleep, growth, and migration. Seasonal changes in day-length cue flowering, leaf fall, and breeding across countless species. From the oxygen in each breath to the grain in each harvest, daily life is threaded with solar energy. A single star illuminates and sustains a biosphere, its steady radiation quietly underwriting the chemistry of life. Light defines the universe's ultimate speed limit. Light in empty space moves at a fixed speed that no signal or material object can exceed. This constant value does not depend on the motion of the source or the observer, a fact that forces space and time to adjust so that all measurements remain consistent. As an object approaches this speed, time for that object dilates relative to an outside frame and lengths along the direction of travel contract. Experiments with fast-moving particles and precision clocks confirm these predictions. The limit ensures that cause precedes effect throughout the cosmos, preventing paradoxes that would otherwise arise. It also defines horizons beyond which events cannot influence a given location within a given interval. Light is therefore not just illumination, but a principle that shapes the scaffold of reality, setting the pace for every exchange of information. Time and space warp in the presence of light. Relativity teaches that measurements of distance and duration depend on motion and gravitational environment. The speed of light remains the same for all observers, so time and space must flex to accommodate that rule. Fast motion makes moving clocks tick more slowly, and moving rulers measure shorter along the direction of travel. Gravity curves space-time, changing the paths of light and altering the rates of clocks at different heights in a gravitational field. Satellites account for these effects to keep navigation systems accurate. Astronomers exploit them to weigh galaxies and to map the expansion of the universe. These warps are not mere abstractions, but everyday tools embedded in technology and observation. Light is both the messenger and the metric, revealing how geometry and gravity shape the stage on which all physical events unfold. Photons carry energy but have no mass. Photons are the indivisible quanta of light. They transport energy and momentum, yet possess no rest mass. Because of this, they always move at the universal speed limit in a vacuum and never come to rest. When photons strike matter, they can push on it, transferring momentum and creating radiation pressure. Over long periods, that gentle force shapes comet tails, clears dust from stellar neighborhoods, and can propel reflective sails on spacecraft. Photons also exhibit polarization and can carry structured forms, such as orbital angular momentum, expanding the ways information can ride on light. In quantum experiments, single photons interfere with themselves and become entangled with partners, revealing that information can be delicately encoded in phase and polarization. Every glint, glow, and ray is a stream of these massless messengers, each one a small packet of energy bridging empty space. A single photon can trigger the human eye. The human visual system can respond to the faintest glimmer nature offers. Inside the retina, rod cells hold light-sensitive molecules that change shape when they absorb a single photon. That tiny rearrangement launches a cascade of chemical steps that amplify the signal many times until it becomes an electrical message sent toward the brain. Under carefully controlled conditions, people can sense brief flashes that correspond to a single quantum of light entering the eye. This level of sensitivity makes sense for a species that often moved at dawn and dusk, when illumination is scarce and every hint of motion matters. It also shows how biological systems push noise to the background, so that genuine signals can rise above random fluctuations. A single photon may have crossed interstellar space or scattered from a nearby wall, yet its arrival can become a real sensation. Energy becomes perception, and the smallest possible packet of light completes a journey into awareness. Some animals can see in near-perfect darkness. Nocturnal life is filled with solutions to the problem of scarce light. Owls and cats enlarge their pupils dramatically and use a reflective layer behind the retina to give every wandering photon a second chance to be detected. Sharks and alligators rely on similar structures that return light through photoreceptors for another pass, improving sensitivity without adding noise. Deep-sea fishes display oversized eyes, tuned to the blue-green glow of bioluminescence. Certain snakes and beetles detect infrared warmth from living bodies, allowing them to locate prey even when visible light is absent. Moths and other night flyers navigate by polarization patterns that remain readable under starlight. Many of these eyes produce a visible shine because returning light exits along the same path it entered. What appears as uniform darkness to human observers is, for these animals, a detailed world of edges, motion, and contrast created from a handful of gathered photons. The Milky Way glows as the light of billions of stars blends together. On a clear night far from city lamps, the Milky Way stretches across the sky like a pale river. That soft band is not a cloud at all, but the combined glow of innumerable stars that lie along the plane of our galaxy. Each distant sun is too faint to distinguish on its own, yet together they create a continuous sheen. Dust grains suspended between stars soften and redden the light, sketching dark lanes and gentle swirls that trace the structure of the spiral arms. Through binoculars or a modest telescope, the haze breaks into packed star fields and hidden clusters. The photons reaching your eyes began their travels long ago, crossing the neighborhood of the sun and then spilling into our atmosphere. The Milky Way is the inside view of our galactic home, a luminous cross-section of a stellar city whose lights have been shining for ages. Light needs no medium to travel through space. Sound depends on air, and ripples on a pond depend on water. Yet light requires nothing but space itself. It is a self-sustaining disturbance made of electric and magnetic fields that continually generate one another as they move. This property allows sunlight to cross the wide emptiness between the sun and Earth without assistance. Early ideas proposed a universal ether as a carrier, but careful measurements showed that no such substance exists. Light does not hitch a ride on matter. it is its own traveler. Because of that independence, light can carry energy and information across the void, linking planets and stars with a silent exchange. Every sunrise proves that waves can move through true emptiness, and every star visible at night confirms the same principle across far greater distances. The universe does not need a medium for light. Space itself is enough. Mirrors reflect light in perfect symmetry. A mirror follows a simple rule. The path into the surface and the path out of it make equal angles with the plane of the mirror. That balance creates the familiar image that seems to live on the far side of the glass. It is not left and right that are reversed, but front and back, a swap determined by the direction the light travels. The quality of a mirror depends on smoothness at scales far smaller than a human hair. When the surface is polished to that standard, incoming rays remain organized, and the reflection carries fine detail. Telescopes rely on large mirrors to gather weak starlight, while microscopes use precision mirrors to build and guide images of tiny structures. Even a household mirror demonstrates the same geometry. Photons leave your face, strike the reflective layer, and return almost immediately, drawing a true picture with nothing more than angle and symmetry. Some mirrors reflect invisible ultraviolet or infrared light differently. A mirror that looks ordinary in daylight can behave very differently when viewed outside the visible spectrum. Coatings that are brilliant in ultraviolet may be dull in the colors we see, and surfaces that shine in infrared can appear flat to human eyes. Engineers exploit these differences by designing multi-layer coatings that stack thin films to reinforce some wavelengths and cancel others. Infrared mirrors guide heat-sensing instruments and move laser beams used in measurement and communication. Ultraviolet mirrors help spectrographs isolate energetic processes in stars and in laboratory plasmas. Even window glass transmits and blocks different parts of the spectrum in ways that influence building temperature and comfort. Reflection is not a single behavior. It is a set of interactions between light and matter that depends on wavelength, angle, and material structure. By tailoring those factors, mirrors reveal or conceal worlds that lie beyond ordinary sight. Polarized light reduces glare and sharpens clarity. When light reflects from water, pavement, or glass, the waves tend to line up along a common direction. That alignment produces harsh glare that washes out color and detail. Polarizing filters correct this by blocking waves in one orientation while letting the rest pass, which reduces reflection and restores contrast. The effect can be dramatic at a lake or along a road on a bright afternoon. Photographers use the same principle to deepen blue skies and to see through surface reflections to what lies beneath. Many animals, including insects and birds, can detect polarization directly. They use it to find water, to navigate by sky patterns, and to communicate with signals that remain invisible to other species. Scientists place stressed plastics and crystals between crossed polarizers to reveal internal strain fields. Polarization is not about brightness or color alone. It is an additional channel of information that light quietly carries. Light can interfere with itself to create beautiful patterns. Combine two coherent beams of light, and the result is not simple addition. Where crests meet, crests the brightness increases, and where crests meet troughs, the light cancels, leaving darkness. This interference creates the shifting rainbows seen on soap bubbles and oil films, where thin layers cause reflections to overlap with slightly different path lengths. The same principle gives peacock feathers and beetle shells their shimmering colors, born from microscopic structure rather than pigment. In laboratories, interference is a measuring tool of extraordinary precision, capable of detecting changes smaller than an atom. It is also a window into quantum behavior, since individual photons sent one at a time can still produce an interference pattern over many trials. The world is full of these subtle maps drawn by overlapping waves. Each pattern is a record of path differences that turns pure geometry into visible form. Lasers produce perfectly aligned light waves. Ordinary light is a crowd of waves moving in many directions and at many frequencies. Laser light is a disciplined procession. Inside a laser, a prepared material stores energy in atoms or molecules. When one photon of the right color passes by, it triggers its neighbors to emit identical photons. Mirrors at the ends of the device send the growing beam back and forth, reinforcing order until a narrow, coherent stream exits through a small opening. Because the waves share the same color and phase, the beam stays tight over long distances and can be focused to an extremely small spot. That combination of direction, uniform color, and stability makes lasers indispensable in scanning, surgery, communication, and precision measurements. The principle is simple. Encourage identical photons to travel together, and they behave with unity, turning light into a tool that carries accuracy wherever it goes. A laser's name comes from light amplification by stimulated emission. The familiar word is actually a compact description of how a laser works. Energy pumped into a material leaves its atoms primed to emit light. When a passing photon matches the stored energy, it stimulates the atom to release an identical photon. That copy can trigger another, and so on, creating a growing population of perfectly matched quanta. Mirrors reflect the light many times through the active material, so amplification builds rapidly. Finally, the beam escapes through a partially reflective mirror as a steady stream or a short pulse. The idea grew from radio and microwave technologies that used similar stimulation at longer wavelengths, then moved into the realm of visible and infrared light. Today, lasers appear in devices as familiar as barcode scanners and as advanced as gravitational wave detectors. The name remains a precise and elegant summary of a profound physical process. Laser beams can cut steel or heal the human eye. Coherent light can be gentle or fierce depending on how it is tuned. In factories, high-power beams focus onto metal, where they deposit energy fast enough to melt and vaporize a narrow groove, while leaving surrounding material largely unaffected. The same control allows clean welds and delicate engraving. In clinics, much lower power beams reshape the cornea to correct vision, seal blood vessels to stop bleeding, or selectively remove damaged tissue. The key is choosing the right color, intensity, and duration so that the target absorbs light efficiently, while nearby structures do not. Because lasers can deliver energy with exquisite spatial and temporal precision, they turn light into a tool for both craft and care. The unity of the beam born from synchronized photons becomes a means to shape matter safely and predictably. The first laser used a ruby crystal to create pure light. The earliest working device that produced coherent visible light relied on a synthetic ruby rod. A bright flash lamp excited chromium atoms inside the crystal, placing them in an energized state. When one photon of deep red color emerged, it stimulated others to follow with the same wavelength and direction. Mirrors on the ends sent the light back through the crystal, increasing the effect until a slim beam escaped. Although modest in power, that moment proved that stimulated emission could be harnessed to generate a coherent beam. The demonstration took light from a phenomenon to a technology. From that ruby red spark came many families of lasers using gases, semiconductors, dyes, and fibers. Each new medium extended the range of colors and powers available. The path from a single crystal to a global tool began with a simple principle and a carefully polished rod. Lasers can trap microscopic particles in place, A tightly focused beam can hold a tiny transparent object steady, as if the light had invisible fingers. The intensity is slightly greater near the center of the focus, and the particle experiences a force that draws it toward that region. By moving the focus, scientists can steer the object with remarkable precision. These optical tweezers have become essential in biology and soft matter physics. Researchers measure the springy response of DNA, observe the motors that walk along cellular scaffolding, and examine the behavior of droplets and colloids. The forces involved are tiny, yet they are sufficient to counter gravity and random thermal motion for objects on the scale of cells and viruses. The technique shows that photons carry momentum and can transfer it in ways that become useful. Light, which we normally associate with seeing, becomes a tool for gently holding and measuring the living world. Atoms can absorb and release light millions of times per second. Electrons in atoms occupy distinct energy levels. When a photon with the right energy arrives, an electron can step up to a higher level by absorbing it. The excited atom soon drops back down, emitting a new photon whose color depends only on the difference between levels. Under steady conditions, atoms repeat these events extremely rapidly, creating the steady glow of lamps, flames, and stars. Each element has a unique set of possible jumps, which means each one leaves a distinctive pattern in the spectrum of emitted or absorbed light. Scientists use those signatures to identify materials in laboratories and to analyze the atmospheres of distant worlds. The constant exchange between electrons and photons drives much of the visible universe. From neon signs to the aura of a nebula, the scene is set by countless rapid transitions, writing color into the darkness. The sun's light contains hidden lines that reveal its elements. Spread sunlight into a rainbow with a prism, and you will see dark lines crossing the colors. Each line marks a wavelength that atoms in the solar atmosphere have absorbed. The set of lines acts like a fingerprint for the elements present. By matching those patterns to laboratory measurements, scientists determined that the sun is made mostly of hydrogen and helium, with smaller amounts of other elements. Slight shifts in the positions of the lines reveal motions in the solar surface and in the layers above it. This method, called spectroscopy, allows a detailed understanding of the sun without touching it. The same approach works for stars across the sky and for planets with thin atmospheres. A beam that looks uniform contains a code. Read the code, and you learn the chemistry and motion of the source, all revealed by missing colors in a spectrum. Astronomers decode the composition of stars through their light. Every star broadcasts information in the light it emits. When that light is dispersed, the spectrum shows bright and dark features tied to specific elements and physical conditions. From those patterns, astronomers infer temperature, surface gravity, and chemical makeup. Small shifts in wavelength betray motion toward or away from us, and can even reveal the tug of orbiting planets. This is a triumph of remote sensing. Without traveling to a star, we learn its character by reading the signatures imprinted on its glow. The method works across the universe, from hot blue giants to cool red dwarfs, and from blazing nebulae to the faint halos of galaxies. Light is not only illumination, it is a messenger that carries precise clues from places no spacecraft can reach. With careful instruments and patient analysis, the night sky becomes a library written in spectra. Some distant planets reveal themselves by dimming their stars. A planet that passes in front of its star briefly blocks a small portion of the starlight. Sensitive instruments record these slight dips as repeating patterns. From the depth and duration of each event, astronomers estimate the size of the planet and the scale of its orbit. Sometimes the starlight filters through the planet's atmosphere during the crossing, imprinting faint features that reveal gases such as water vapor or methane. The technique has uncovered thousands of worlds, including small rocky planets and large giants that skim close to their suns. It proves that planetary systems are common and diverse. The transit method turns a barely perceptible change in brightness into a map of unseen companions. Light that fades and brightens by a tiny fraction becomes evidence of another world circling far away, a gentle rhythm that points to places we may one day explore. Light carries information through glass fibers across oceans. Beneath the waves, bundles of glass fibers span continents and carry much of the world's communication. Inside each strand, light is confined by total internal reflection, bouncing along the core with minimal loss. Data rides on that light as rapid changes in intensity or as separate colors that share the same path. Repeaters along the route restore the signal without turning it back into electricity, so efficiency remains high over great distances. Compared with metal wires, fibers suffer little interference and produce almost no heat. They are thin, flexible, and capable of immense capacity. Messages that begin as electronic impulses inside computers and phones become streams of photons racing through darkness under cold, crushing pressure. The quiet glow within those fibers stitches together markets, families, research teams, and friends. It is a global nervous system whose impulses are patterns of light. A single fiber optic strand can carry billions of conversations. One hair-thin thread of glass can transport staggering amounts of information. The trick lies in sending multiple colors at once, each acting as an independent channel. This approach, called wavelength division multiplexing, turns a single strand into a bundle of parallel paths. Because light waves ignore ordinary electrical crosstalk, the channels remain clean, even when packed together. Optical amplifiers placed along the route boost all the colors simultaneously. The result is a capacity that dwarfs older systems based on copper. Across cities and under oceans, these strands move phone calls, video streams, medical data, and scientific measurements with ease. The fiber does not care whether the payload is a conversation, a symphony, or an image from a distant telescope. It simply guides organized light from place to place. Civilization speaks in photons, and a strand no thicker than a hair carries the chorus. Light travels farther and faster than electricity in copper. Electrical signals in metal face resistance and capacitance that slow them and waste energy as heat. Photons moving through glass or air encounter no such drag. They glide forward at the universal speed limit for information and maintain clarity over long distances. That is why long-haul communication favors optics. Streams of light keep their timing tight and their bandwidth wide. They ignore many of the distortions that plague currents in wires. Satellites link with ground stations using beams that cross the sky in an instant. Laboratories synchronize distant clocks by sharing pulses of light through fiber. The same property that lets starlight cross the void powers human networks. When information rides on photons instead of electrons, it arrives sooner and cleaner. The world's nervous system runs on light because nothing natural moves information more swiftly or with greater grace. Soap bubbles shimmer with colors from interfering light waves. A soap bubble's color is not a tint of pigment, but a dance of reflected light. The bubble's wall is an impossibly thin film of water trapped between two layers of soap molecules. When sunlight hits it, some light bounces from the outer surface, and some travels through the film, reflects from the inner surface, and meets the first reflection again. Depending on the film's thickness and the wavelength of the light, the two reflections interfere, amplifying certain colors and canceling others. As the film drains and thins, the colors shift from green to pink to violet before the bubble finally vanishes. Every shimmer is a momentary balance of wave paths, measured in billionths of a meter. The patterns have inspired physicists, artists, and mathematicians alike. Within a single floating bubble, light performs its purest form of art, creating color out of geometry, movement, and air. Butterfly wings create color through microscopic structures. Many butterflies display colors that never fade because they are not made from dyes, but from structure. Under a microscope, their wing scales reveal tiny ridges and layers that act as diffraction gratings. These microstructures split and scatter incoming light, selecting specific wavelengths to reinforce while others cancel. The result is a hue that depends on the physical spacing of the ridges rather than on chemicals. Unlike paint, this kind of coloration does not degrade over time, which is why ancient specimens in museums still gleam as brightly as when they flew. Structural color also changes with viewing angle, giving butterflies their iridescent sheen. Scientists study these wings to design new materials for anti-counterfeiting patterns, solar cells and vivid displays that require no pigment at all. In the quiet flutter of a wing, nature shows how pure geometry can conjure color from light itself. Hummingbird feathers change color as they catch the light. A hummingbird's feathers seem to shift from emerald to sapphire to ruby as it moves. Yet those hues do not come from pigments. Each feather contains stacks of microscopic platelets made of keratin and air, arranged so that they act like tiny prisms. As light strikes the feathers at different angles, certain wavelengths interfere constructively and others cancel, creating colors that vary with motion and viewing direction. This optical effect, called iridescence, makes hummingbirds appear to glow with living jewels. The colors also play a role in communication and courtship, where small changes in angle reveal flashes of brilliance invisible from other perspectives. Scientists studying these feathers have learned to reproduce similar structures in laboratories, leading to materials that mimic the bird's shifting light. Every beat of a hummingbird's wings is a demonstration of physics transformed into living art. The morpho butterfly's blue comes from light, not pigment. The dazzling blue of the morpho butterfly has no pigment whatsoever. Instead, the color arises from microscopic structures on its wings that manipulate light through interference. Each scale on the wing contains layers of chitin spaced just right to reflect blue wavelengths while cancelling others. The effect is so strong that a single butterfly can be seen from far away in the rainforest canopy. When the angle changes, the hue shimmers and fades, revealing a metallic depth that no dye could reproduce. Engineers have studied the morpho's wings to develop anti-counterfeiting features, sensors, and fabrics that change color with light. The secret lies not in chemistry, but in nanostructure, a natural photonic crystal designed by evolution. When sunlight passes over the wings, it becomes sculpted into blue itself, a color born purely from the physical language of light. Diamonds sparkle because light bends and reflects inside them. The fire of a diamond comes from the way it bends and splits light. When a ray enters the stone, it slows and changes direction because the material has a high refractive index. Inside, the light reflects off the inner faces, bouncing repeatedly before escaping through the top facets. Each bounce disperses the light into its component colors, producing tiny flashes of red, blue, and green. The geometry of the cut determines how efficiently the light returns to the eye. A well-cut diamond channels most of the incoming light back outward, maximizing brilliance, while a shallow or deep cut lets it leak away. The sparkle is a conversation between optics and geometry, between angle and brilliance. Every glint is a message from photons that entered the crystal and ricocheted within it before returning as tiny spectral fireworks. Stars twinkle because Earth's air distorts their light. The steady light of a star begins its journey as an unbroken beam, but when it reaches Earth, it must pass through layers of shifting air. Each layer has a slightly different temperature and density, bending the light in unpredictable ways. The result is a constant dance of refraction that makes the star appear to flicker and change color. Planets, which show a broader disk rather than a single point, seem steadier because their light averages out these distortions. Astronomers correct for the effect using adaptive optics, where mirrors deform in real time to cancel the turbulence. Above the atmosphere, space telescopes escape this shimmering altogether, revealing stars as they truly are, steady and precise. Twinkling is not a property of the stars themselves, but of the living, breathing atmosphere of our own planet, playing with their ancient light. Space telescopes see clearly because they orbit above the atmosphere. On Earth, the air bends, scatters, and absorbs light, blurring the view of the cosmos. Space telescopes rise above this turbulent layer, giving them an unobstructed window into the universe. Freed from distortion, their instruments capture details invisible from the ground: faint galaxies, sharp planetary surfaces, and the glow of distant nebulae. In orbit, they can also observe wavelengths that never reach the surface, such as ultraviolet and infrared. Each mission must balance exposure to sunlight, extreme cold, and the challenge of maintenance, far from human hands. Yet the reward is immense. Space telescopes return images so crisp that they change our understanding of cosmic structure. When you see a photograph of a galaxy or nebula filled with clarity and depth, you are seeing light that arrived unscattered, untouched by earthly air, and recorded in its purest possible form. The Hubble telescope captures light that began its journey billions of years ago. The Hubble Space Telescope floats in silent orbit, patiently collecting light that has traveled for billions of years. Each photon it detects began its journey when galaxies were young and stars were newly born. Because light takes time to travel, distant objects appear to us as they once were, not as they are now. Hubble's mirrors and instruments act as time machines, revealing the early structure of the universe. Some of the faintest smudges in its images represent galaxies forming less than 1 billion years after the Big Bang. These ancient signals arrive one photon at a time, yet when gathered over long exposures, they create portraits of creation itself. The telescope's precision optics and stable environment above Earth's atmosphere let it capture details smaller than a pinhead seen from miles away. Through Hubble's gaze, light becomes history written across the sky. Expanding space stretches light into longer, redder waves. As the universe expands, it stretches not only the distance between galaxies, but also the very light traveling through it. Waves of light lengthen during their journey, shifting toward the red end of the spectrum. This redshift acts as a cosmic fingerprint of motion, allowing astronomers to measure how quickly galaxies are moving away from one another. The farther the source, the more stretched its light becomes, which means we see ancient galaxies not only as they were long ago, but also in hues shifted by the growth of space itself. The effect is not caused by movement through space, but by the expansion of space between points. The color of distant light thus tells the story of the universe's evolution. Every red glow from the depths of the cosmos is a message from light that has been gently pulled across time itself. Distant galaxies appear red because the universe is growing. When astronomers look deep into the cosmos, they find that the most remote galaxies glow in shades of red. This is not because they are inherently red in color, but because their light has been stretched as space expands. The process, known as cosmological redshift, lengthens each photon's wavelength as it travels toward us. The degree of redshift reveals the galaxy's distance and speed of recession, forming the foundation of modern cosmology. Observing this pattern confirmed that the universe is not static, but evolving. with galaxies drifting ever farther apart. In this way, color becomes a measure of time and expansion. The red light reaching our telescopes is ancient and weary, stretched by billions of years of travel. Within it lies proof that the cosmos itself is dynamic, a living fabric that grows even as we measure it. Light experiences no time as it travels. For light, the passage of time does not exist. A photon moves through space at the ultimate cosmic speed limit, and according to relativity, time slows to a complete standstill from its perspective. The moment it leaves a source and the moment it arrives somewhere else are the same instant in its own frame of reference. While ages may pass for observers, the photon's journey is timeless. This strange truth means that the light striking your eyes from a distant star began its existence and fulfilled its purpose in one continuous act. Space and time are intertwined, and light travels along the edges of that union where duration collapses. Every ray of sunlight or starlight you see is both ancient and immediate. It carries no memory of the voyage because, in a sense, for light, the voyage never happened at all. For a photon, departure and arrival happen in the same instant. From the perspective of a photon, the universe is compressed along its line of travel. The distance between emission and absorption shrinks to nothing, and time itself becomes meaningless. When light leaves the surface of a star and later touches your retina, what feels to us like a journey of years is, for the photon, one continuous event. Einstein's theory of relativity allows this paradox, showing that at light speed, both time and distance lose their ordinary meaning. This concept changes how we think about connection and separation. The light from distant galaxies has crossed unimaginable expanses, yet for the photons themselves, there was no interval between beginning and end. Each beam we see is an instantaneous bridge between origin and observer, joining 2 points in space-time without delay. In light's own frame, existence is a single, eternal now. Gravity can bend the path of light around massive objects. Einstein predicted that gravity would curve not only the motion of planets, but also the paths of light itself. When a beam passes near a massive object, such as a star or galaxy, the surrounding space-time bends, and the light follows that curve. The effect was first confirmed when starlight grazed the sun during an eclipse, appearing slightly shifted from its usual position. In the wider cosmos, this bending can focus and magnify distant galaxies, turning them into distorted arcs of light. The phenomenon shows that light travels along the geometry of space rather than through an invisible force field. Gravity sculpts those paths, revealing the shape of the universe's invisible fabric. Each time astronomers observe a curved or duplicated image in the sky, they are watching space-time act as a lens, guiding light along routes written by mass itself. Gravitational lensing lets us see hidden galaxies beyond others. Massive clusters of galaxies act like cosmic magnifying glasses. Their gravity bends and focuses light from objects lying far behind them, creating arcs, rings, and mirrored images. This effect, called gravitational lensing, allows astronomers to study galaxies that would otherwise be too faint or distant to detect. Sometimes the lensing even amplifies the glow of a single star, briefly revealing it across billions of light years. The same principle lets scientists map invisible dark matter, since its gravity contributes to the lensing pattern. What we see through these lenses is a distorted but magnified view of the universe's distant past. Each image is both a picture and a map, showing how mass warps the light that passes nearby. In this way, gravity becomes an instrument of observation, turning entire galaxy clusters into natural telescopes built by the cosmos itself. Light escaping a black hole's edge stretches to infinity. Near the boundary of a black hole, gravity's pull becomes so extreme that even light must fight to escape. Photons that manage to climb away lose energy as they rise, causing their wavelengths to stretch until they become infinitely long at the very edge. To a distant observer, this redshift means that light appears to slow and fade, freezing just before vanishing into darkness. The black hole's event horizon marks the point beyond which no signal can return, yet just above it, light can still struggle outward, bearing the last visible evidence of the matter falling in. This gravitational redshift is a direct expression of relativity, showing that energy and time warp together near intense gravity. The light that does escape carries the final whisper of what once approached the abyss, stretched thin across eternity by the weight of space-time itself. Near black holes, light can orbit in perfect circles. In the region surrounding a black hole lies a strange boundary, where light itself can become trapped in circular paths. This is known as the photon sphere. Here, gravity bends space so sharply that a photon launched tangentially can loop around the hole indefinitely. In reality, even the slightest disturbance sends it spiraling inward or outward, but the orbit remains a theoretical point of balance. Simulations of this region produce the bright ring seen in images of black holes captured by radio telescopes. The glow comes from photons that have circled many times before, finally escaping toward Earth. These rings allow astronomers to measure the size and spin of black holes, turning light into a probe of the most extreme environments known. At the photon sphere, the boundary between motion and imprisonment narrows to a razor edge defined by gravity and geometry. Bent starlight once proved Einstein's theory of relativity. In the early 20th century, Einstein's theory predicted that light passing near the sun would be deflected by a small but measurable amount. During a total solar eclipse, astronomers could test that idea by photographing background stars whose light skirted the darkened sun. When the photographs were compared with star positions taken at other times, the predicted shift was observed exactly as Einstein had calculated. The confirmation transformed him from a theoretical physicist into a global icon and cemented the new understanding of gravity as curvature in spacetime. That experiment showed that even something massless responds to the geometry created by mass. Every subsequent measurement of gravitational lensing traces its roots to that moment, when starlight, bent by the sun's pull, validated one of the most profound insights ever conceived about the nature of reality. Quasars shine brighter than entire galaxies. Quasars are among the most luminous objects in the universe, powered by supermassive black holes at the centers of young galaxies. As matter spirals into these giants, friction and magnetic fields heated to millions of degrees, releasing torrents of light and radiation. The energy is so intense that a single quasar can outshine all the stars of its host galaxy combined. Seen from billions of light years away, they appear as brilliant points, yet they mark the cores of immense cosmic engines. Studying quasars helps astronomers understand how galaxies evolve and how black holes grow. Their light serves as a beacon that illuminates intergalactic space, revealing the distribution of gas and elements between galaxies. Each quasar is a paradox of destruction and illumination, where gravity's hunger transforms falling matter into radiant power that travels across the ages. Gamma-ray bursts are the most powerful flashes of light known. Occasionally, the universe releases a burst of energy so intense that it outshines everything else in the sky for a brief moment. These gamma-ray bursts arise when massive stars collapse into black holes or when neutron stars collide. The resulting explosion emits jets of high-energy photons that race across space, carrying more power in seconds than the sun will emit in its entire lifetime. Detectors in orbit record these events as sudden blazes that fade quickly but leave afterglows across many wavelengths. Each burst offers clues about the violent processes that shape galaxies and forge heavy elements. They remind astronomers that light is not always gentle. Sometimes it arrives as a shout from the cosmos, announcing a transformation so fierce that even from billions of light years away, its radiance cannot be ignored. Each element has a unique light signature like a cosmic barcode. Every atom interacts with light in a distinct way because its electrons occupy energy levels separated by precise intervals. When an atom absorbs or emits photons, the wavelengths involved form a pattern unique to that element. Spread the light from a flame or a star through a prism, and you will see lines of color and darkness that serve as identifiers. This principle, known as spectroscopy, allows scientists to determine the composition of distant stars, nebulae, and galaxies without leaving Earth. Astronomers can even measure how fast an object moves by observing small shifts in those spectral lines. Chemists use the same idea to analyze substances in laboratories, identifying unknown compounds through their light fingerprints. Across the universe, from the core of a furnace to the edge of a galaxy, every element signs its name in the language of light. Old clocks once glowed with dangerous radium light. In the early 20th century, glow-in-the-dark watches and clocks became symbols of modernity. Their numbers and hands shone softly at night without batteries or sunlight. The glow came from a mixture of zinc sulfide and a radioactive element called radium. The radiation from the radium constantly excited the zinc compound, making it emit a gentle greenish light. For years, workers who painted these luminous dials were told the material was harmless. Many even shaped their paintbrushes with their lips to create fine points. Decades later, it became clear that the radiation was slowly poisoning them. The tragedy of the so-called radium girls led to major advances in safety standards, health research, and the understanding of radioactivity's effects on living tissue. Today, glow materials use harmless phosphorescent compounds, powered by absorbed light instead of radiation. The gentle glow of modern dials carries the lessons of a time when beauty outshone caution. Fluorescent lights work by turning invisible rays into visible glow. Inside a fluorescent lamp, light begins as something invisible. An electric current flows through a low-pressure gas, causing it to emit ultraviolet radiation. This radiation strikes a coating of phosphor on the inside of the glass tube, which absorbs the high-energy rays and re-emits them as visible light. The process is efficient, producing bright illumination without the heat of traditional filaments. Each type of phosphor produces slightly different shades of white, allowing manufacturers to tune the color for offices, homes, or studios. The discovery of fluorescence revealed that energy can change form within atoms, bridging the invisible and visible worlds. This principle appears in nature as well, from minerals that glow under ultraviolet light to deep-sea creatures that shimmer with their own fluorescence. When you see a fluorescent lamp flicker to life, you are witnessing an elegant transformation. Invisible energy reshaped into light we can see and use. LEDs produce light by moving electrons across tiny crystals. A light-emitting diode, or LED, creates light through motion at the atomic level. Inside each device, two layers of semiconductor material meet, one rich in electrons, the other lacking them. When electricity flows, electrons cross the junction and release energy as photons. The color depends on the energy difference between the layers, which engineers control by adjusting the crystal's composition. LEDs waste very little energy as heat, making them far more efficient than older lamps. They also last for tens of thousands of hours without burning out. This technology has reshaped lighting, from street lamps to computer screens, and opened possibilities for energy conservation worldwide. The same principle powers tiny indicator lights and enormous video walls alike. What once required glass bulbs and filaments now fits within microscopic chips. Every LED is a small factory where electric potential becomes light in a clean, continuous flow. The sun is actually white when seen from space. From Earth's surface, the sun looks yellow or golden. But that color is an illusion created by our atmosphere. When viewed from space, the sun's light is pure white, containing all visible wavelengths in near equal measure. As sunlight passes through Earth's air, shorter blue wavelengths scatter away, leaving the direct beam slightly warmer in tone. This scattering also explains why the sky appears blue during the day. Astronauts outside the atmosphere describe the sun as brilliant and colorless, shining against a black sky. White light from the sun carries the full spectrum that paints the world with color. Plants, oceans, clouds, and stone all reflect and absorb portions of that balanced radiance. What we call sunlight is not a single hue, but a continuous blend of every visible color. The golden tint we see from below is Earth's gentle modification of a star's true blinding whiteness. Candle flames flicker with subtle currents of air. A candle's glow looks steady from afar, yet up close it wavers constantly. The flicker arises from tiny movements of air that change how oxygen feeds the flame. Each puff of air alters the shape of the burning zone, causing momentary brightening or dimming. Within the flame, soot particles heated until they glow create the familiar golden color, while cooler gases above emit faint blue at the base. The gentle dance of a candle is a balance of combustion, convection, and chemistry. The upward motion of hot air draws in fresh oxygen below, maintaining the flame's life. When the air is still, the flame forms a perfect teardrop when disturbed. It sways like a living creature seeking breath. Every flicker is a visible heartbeat of energy transformation, where carbon and hydrogen meet oxygen to become light, warmth, and invisible traces of vapor. Moonlight can carry a hint of color on snow or water. Though we often imagine moonlight as pure silver, it carries subtle hues shaped by reflection and the landscape. The moon's surface reflects sunlight imperfectly, scattering it with a slightly warm tint. When that light meets Earth's atmosphere, it picks up faint color shifts from dust and moisture. Snow-covered fields scatter it into soft blues, while calm water turns it silvery gray. In forests or deserts, moonlight can seem golden or even greenish depending on surroundings. Because the human eye is less sensitive to color in low light, these variations appear delicate, almost imagined. Yet cameras reveal them clearly. The quiet light we call moonlight is simply sunlight modified by stone, distance, and night air. It shows how reflection transforms character without changing essence. Every moonlit scene is the same sunlight we know by day, filtered through the poetry of night. Volcanic lightning turns ash clouds into glowing storms. During major eruptions, volcanoes sometimes unleash lightning within their towering plumes. The spectacle arises when ash particles and ice crystals collide, exchanging electrical charges. As billions of these grains interact, the cloud becomes a vast generator, separating positive and negative charges until sparks leap through the mixture. The resulting bolts can illuminate the entire eruption column, flashing through billowing smoke and fire. Unlike ordinary thunderstorms, these discharges come from rock and ash rather than water droplets. Each bolt briefly turns molten fragments and gases into a luminous sculpture of plasma. Scientists study volcanic lightning to understand both atmospheric electricity and eruption dynamics, since the flashes can be detected even through thick clouds. When seen from a distance, the sight looks apocalyptic yet beautiful, a reminder that even the most violent forces of geology express themselves through the universal language of light. Some jellyfish pulse with living light in the dark, Drifting in the depths, certain jellyfish create their own glow through bioluminescence. Inside specialized cells, chemical reactions combine oxygen with a light-producing molecule called luciferin, triggered by an enzyme named luciferase. The result is a cold, gentle light that radiates through the creature's transparent body. Some species pulse rhythmically. Others flare suddenly when disturbed, forming luminous halos in the water. The glow may lure prey, confuse predators, or communicate with potential mates. Scientists have studied these proteins to create tools that illuminate biological processes, allowing cells to glow under microscopes. From a drifting jellyfish in the abyss came discoveries that transformed molecular biology. In the ocean's silence, each pulse is both a defense and a declaration, proof that even in the absence of sunlight, life finds a way to write with light upon the dark. Ocean waves can sparkle from bioluminescent bacteria. Along certain coastlines, breaking waves glow with blue fire that brightens and fades with every surge. The phenomenon comes from microscopic organisms known as dinoflagellates, which produce light when disturbed. As waves tumble or footsteps stir the water, chemical reactions inside the cells create short bursts of luminescence. The glow helps deter predators and startles larger creatures that might feed on them. To human eyes, it looks like liquid starlight washing onto the shore. These living lights appear most often in warm, nutrient-rich waters, where the organisms gather in vast numbers. On dark nights, entire bays can shimmer with every motion, turning the sea into a mirror of the heavens. Bioluminescence is a language of defense and wonder, a chemical conversation carried out in photons. The ocean's edge becomes a place where life itself paints moving constellations upon the waves. Fireflies waste almost no energy when they glow. The warm flicker of fireflies on summer nights is one of nature's most efficient light sources. Their glow comes from a chemical reaction inside tiny organs in the abdomen, where oxygen combines with luciferin in the presence of an enzyme. Nearly all of the energy produced becomes light, with almost no heat, a process scientists call cold light. By contrast, incandescent bulbs waste most of their energy as heat. Fireflies use their glow to signal mates, creating complex flashing patterns that vary by species. Some synchronize entire populations into rhythmic waves of light that sweep through forests and fields. Researchers have adapted the biochemistry behind these natural lanterns to develop sensors, medical tracers, and safe glow materials. The firefly's beacon is not only a romantic symbol of night, but also a lesson in perfect efficiency, illumination without waste. Nocturnal eyes reflect light to see in darkness. When a flashlight catches the eyes of an animal at night, the returning glow is more than eerie, it is functional. Many nocturnal creatures have a reflective layer behind the retina called the tapetum lucidum. This layer bounces incoming light back through the photoreceptors, effectively giving each photon a second chance to be absorbed. The result is greatly enhanced night vision. Cats, dogs, deer, and many other animals share this feature, which produces the ghostly eye shine familiar to anyone driving along dark roads. The color of the reflection varies with the animal and the angle of view, ranging from green to yellow or white. This adaptation allows creatures to navigate, hunt, and survive in near darkness where humans would see nothing. The gleam in their eyes is both practical and haunting, a living reflection of light's persistence, even in the shadows. Human skin senses light even through closed eyelids. Though our eyes are the main organs of vision, the skin also responds to light in subtle ways. Cells beneath the surface contain receptors sensitive to brightness that help regulate circadian rhythms and hormone production. When light penetrates closed eyelids, it signals the body that day has arrived, influencing sleep cycles and mood. Experiments have shown that exposure to light, even without visual input, can shift the body's internal clock. The effect is especially strong for blue wavelengths, which are most effective at resetting circadian timing. This sensitivity explains why people sometimes wake earlier when morning sunlight fills a room, even before opening their eyes. The skin and brain together form a network attuned to the rhythm of daylight. Light is not only something we see, but also something we feel, guiding the body's internal sense of time and renewal. The brain adjusts to new light levels in seconds. Step from sunlight into a dim room and, for a moment, everything seems invisible. Within seconds, your eyes and brain recalibrate. Pupil size changes first, shrinking or expanding to control how much light enters. Then, chemical processes in the retina adjust the sensitivity of rods and cones. The brain interprets these signals and corrects contrast to create a stable image. This rapid adaptation allows humans to move between night and day without losing perception. It is a dynamic process, constantly balancing brightness and shadow. Without it, the world would flash between blinding glare and total blackness. The ability to adapt quickly to new illumination shows how deeply the nervous system is synchronized with the environment. Even before conscious awareness returns, the visual system has already rewritten its settings, ready to perceive light once more in perfect balance. Sunlight triggers the hormone that lifts our mood. Exposure to sunlight stimulates the release of serotonin, a neurotransmitter associated with mood and focus. Specialized cells in the retina detect daylight and send signals to brain regions that regulate hormone production. When days shorten in winter, reduced light can lower serotonin levels, leading to fatigue or melancholy. Some light also suppresses melatonin, the hormone that promotes sleepiness, helping to align the body's rhythm with the day-night cycle. This connection between light and chemistry explains why spending time outdoors often improves energy and outlook. Even a few minutes of morning sunlight can reset the biological clock and enhance alertness. The relationship is ancient. Long before artificial light, human health depended on the rising and setting of the sun. Every beam that touches the skin or eye carries more than warmth. It carries the information the brain needs to maintain emotional equilibrium. Blue light from screens can disrupt the body's sleep rhythm. The glow of electronic screens mimics the color balance of daylight, particularly the strong blue component that signals wakefulness to the brain. When viewed late at night, this light suppresses melatonin production and confuses the body's natural rhythm. The result can be difficulty falling asleep and a restless night. Blue light is not harmful in itself. It is essential for daytime alertness, but timing matters. Many devices now include filters that shift the emitted spectrum toward warmer tones after sunset. Scientists advise limiting screen exposure before sleep or using dimmer amber lighting in the evening. The lesson is ancient, yet newly relevant. The body listens closely to light. By matching our technology to the natural cycle of day and night, we preserve the balance that evolution built. Healthy rest begins not only with quiet, but with darkness that tells the brain it is time to dream. The color of light changes how we feel. Color carries emotional weight as well as visual information. Warm hues such as red and amber evoke comfort and intimacy, while cool blues and greens suggest calm or melancholy. These responses arise from both biology and culture. Long wavelengths of warm light stimulate the nervous system gently, increasing heart rate slightly and drawing attention inward. Shorter, cooler wavelengths signal openness and distance, mimicking the color of the sky and sea. Artists, architects, and therapists use this knowledge to shape environments that soothe or energize. In hospitals, daylight-balanced light supports healing and alertness in homes. Warmer tones encourage rest. Every illumination influences mood, focus, and even the perception of time passing. Light does not only reveal objects, it shapes experience itself, painting our emotions with wavelengths that reach from the external world deep into the nervous system. Warm and cool light set the mood in art and film. Cinematographers and painters have long used color temperature to control emotion. Warm light with golden or reddish tones conveys intimacy, nostalgia, or safety. Cool light, tinged with blue, evokes isolation, tension, or stillness. These differences come from how the human eye and brain interpret the balance between short and long wavelengths. Morning and evening sunlight tend to be warm because the rays pass through more atmosphere, while midday light is cooler and more neutral. Artists mimic these variations to direct feeling and attention. In film, a scene lit with warm hues may suggest love or memory, while the same setting under cold light becomes detached and somber. The science of color temperature blends seamlessly with storytelling, showing that perception of warmth and cold extends beyond touch. Light becomes emotion made visible, capable of turning space into mood and time into feeling. Light pollution hides most of the stars from urban skies. In large cities, streetlights, signs, and windows create a dome of brightness that washes out the night sky. The scattered light reflects from dust and moisture in the air, reducing contrast until only a few of the brightest stars remain visible. Astronomers call this glow sky glow, and it extends far beyond city limits. The loss is more than aesthetic. It disrupts ecosystems and confuses migratory animals that navigate by starlight. Efforts to reduce light pollution include shielding lamps to direct light downward and using lower color temperatures that minimize blue scattering. When such measures are applied, stars reappear and nocturnal wildlife flourishes. In remote places untouched by artificial glare, the Milky Way still arches bright enough to cast faint shadows. The stars are always there, hidden not by clouds but by our own excessive illumination, waiting for darkness to return and reveal them again. Astronomers use filters to reveal hidden details in light. Telescopes often capture more than what the human eye can see. By placing filters in front of their detectors, astronomers isolate specific wavelengths that correspond to different physical processes. One filter might show the glow of hydrogen gas, another the light from oxygen or sulfur. Combining these filtered images reveals structures invisible in plain view, such as shock fronts in nebulae or star-forming regions within galaxies. The same technique helps researchers detect planets, measure temperatures, and trace magnetic fields. On Earth, photographers use similar filters to reduce glare or enhance contrast, but in space science the effect is revelatory. What appears as empty blackness in ordinary light can blaze with detail under a chosen wavelength. Filters teach us that light is not a single image but a layered story, waiting to be separated into its many voices and read anew. Plants bend toward light through phototropism. When a plant grows toward a window, it is responding to the unequal distribution of light on its surfaces. Cells on the shaded side elongate more than those on the bright side, causing the stem to curve toward illumination. The process is controlled by plant hormones called auxins, which migrate away from light and stimulate growth where it is dimmer. Phototropism ensures that leaves and shoots position themselves to capture the most energy for photosynthesis. The same principle helps roots orient downward, following gravity instead of light. Experiments have shown that even seedlings kept in complete darkness retain the ability to detect faint light cues once exposed. The graceful turning of a sprout toward a sunbeam is not a random motion, but a finely tuned reaction to the physics of light. It is nature's quiet choreography of growth and illumination. Seeds sense light to know when it is safe to sprout. Before a seed dares to awaken, it measures the world around it through light. Hidden within its outer shell are photoreceptor molecules that respond to different wavelengths. Red light often signals open ground and sunlight, while far-red light indicates shade or burial beneath soil. When the balance between these signals suggests that conditions are right, the seed activates genes that begin germination. Visibility ensures survival by preventing growth when sunlight would be blocked or fleeting. Farmers use controlled lighting to trigger uniform sprouting, while ecologists study how forest canopies filter the wavelengths that guide this decision. Even in apparent dormancy, the seed listens to the language of light. What seems lifeless is in fact alert, waiting for the subtle cue that says, now is the moment. Light does not just nourish the grown plant, it tells the seed when to start its story. Photosynthesis turns sunlight into the breath of life. Green leaves perform one of the most elegant transformations in nature. They turn sunlight into chemical energy. Within each chloroplast, molecules of chlorophyll capture photons and use their energy to split water into hydrogen and oxygen. The hydrogen combines with carbon dioxide to form sugars, while the oxygen is released into the air. This process, photosynthesis, powers nearly every food chain on Earth. The energy you use to move, think, and breathe can be traced back to sunlight, stored in plant matter. Even the fuels that drive engines and heat homes come from ancient photosynthesis buried as coal and oil. The reaction is astonishingly precise, balancing light capture, electron transfer, and molecular assembly in quiet perfection. Every green field and forest canopy is a living solar array. Through this dance between light and leaf, the sun's radiance becomes the breath and heartbeat of the planet. Even faint starlight can push spacecraft with gentle pressure. Light carries momentum despite having no mass. When photons strike a surface, they impart an almost imperceptible push. Over time, and across large areas, this push becomes measurable. Engineers have used this property to design spacecraft that adjust orientation or trajectory without fuel, simply by angling reflective panels toward or away from sunlight. Though the force is delicate, far lighter than a feather, it continues constantly. In the vacuum of space, where there is no friction, even this whisper of pressure can accumulate. Astronomers also notice its effects on cosmic dust, as particles drift outward from the sun in slow spirals driven by photon pressure. The same principle explains the shimmering tails of comets, blown gently by sunlight. In every beam, energy and momentum travel together, proving that light is not only illumination, but also touch. A steady hand, capable of moving worlds across emptiness. Solar sails use light alone to glide through space. Imagine a spacecraft with no engine, no exhaust, and no sound. Only vast reflective sheets catching sunlight. This is the concept of the solar sail. By reflecting photons, the sail captures their momentum and converts it into continuous thrust. Although the acceleration is tiny, it never ceases, allowing the craft to build speed steadily over weeks and months. Missions have already demonstrated this quiet propulsion, proving that sunlight can serve as a cosmic wind. Future explorers may use solar sails to reach distant planets, asteroids, or even nearby stars, gliding gracefully on the pressure of light itself. The technology echoes ancient seafaring, trading water for space and wind for photons. With no need for fuel, a solar sail could travel indefinitely, turning every sunrise into a gentle push forward. Light becomes both map and movement, a luminous breath carrying human curiosity into the deep. The sun sends more energy in an hour than humanity uses in a year. Every minute, the sun floods Earth with a torrent of energy so vast that only a fraction is ever captured. In a single hour, enough sunlight reaches the planet's surface to power human civilization for an entire year. Most of it warms oceans, fuels weather, and drives the photosynthesis that sustains life. The rest is reflected back into space or absorbed by clouds and air. Modern solar technology seeks to harness a small portion of this abundance, converting photons into electricity through photovoltaic cells. Even modest increases in efficiency could transform how we meet global energy needs. The scale is humbling. All the fires of industry and the glow of cities are dwarfed by what the sun provides effortlessly. Light is the planet's true inheritance, endless, silent, and generous beyond comprehension, falling freely upon every leaf, rooftop, and sea. Mirrors can focus sunlight so intensely they melt metal. When light is gathered and concentrated, it becomes a powerful force. Curved mirrors and lenses can focus sunlight onto a small point, raising temperatures high enough to melt steel or ignite stone. Ancient civilizations used polished bronze or obsidian to start fires in rituals and signal over long distances. Today, solar furnaces and power plants use fields of mirrors to concentrate sunlight onto towers that heat fluids and drive turbines. The principle is identical. Bring many rays together, and their energy unites into extraordinary intensity. At the heart of a solar focus, matter glows white-hot, and metals flow like wax. Yet a slight shift of angle disperses the heat instantly, returning it to harmless light. The experiment reveals the dual nature of sunlight. It can nurture or destroy, depending on how it is gathered. Focused light is the sharp edge of radiance itself. Ancient cultures used polished stone to start fires with light. Long before lenses and mirrors were perfected, ancient peoples discovered that polished crystals could concentrate sunlight. Clear quartz, obsidian, and bronze were shaped into curved forms that brought distant rays to a single burning point. In temples and sacred rituals, priests used these tools to ignite fires, symbolizing divine power descending from the sun. Archaeological evidence suggests that cultures from Greece to Mesoamerica practiced this art, linking flame and light as expressions of creation. The act of lighting a fire from the sun carried both practical and spiritual meaning, uniting heaven and earth through energy alone. Later, scientists used similar principles to build early optical instruments, tracing the lineage from sacred flame to telescope. Each shining spark born from a polished stone was a moment when human ingenuity met the cosmos, turning sunlight into a bridge between the natural and the divine. The brightness of stars has been measured since ancient times. Long before telescopes, observers classified stars by brightness, noting which shone most powerfully and which barely pierced the darkness. The Greek astronomer Hipparchus established one of the first brightness scales, grouping stars into 6 levels visible to the naked eye. Modern measurements still use a system based on those early observations, refined into the magnitude scale used today. This continuity across millennia shows how careful watching can evolve into science. What once was judgment by eye has become quantifiable precision, with sensitive detectors measuring differences in luminosity too small for human perception. Brightness reveals more than visibility. It tells astronomers about distance, temperature, and energy output. The stars have not changed, but our ways of reading them have grown more exact. Across history, light has been our most reliable teacher, a constant companion from the first sky watchers to the space telescopes of the present. Every photon carries a tiny twist of angular momentum. Light not only moves forward, it also spins. Each photon carries a small amount of angular momentum, meaning it can exert a twisting force when absorbed or reflected. This property, known as spin angular momentum, arises from the circular polarization of light waves. In laboratories, scientists have used this subtle twist to rotate microscopic particles, trap atoms, and probe quantum systems. Even though the momentum of a single photon is minuscule, the collective effect of many can be significant. Understanding light's angular momentum has opened new fields, such as optical manipulation and quantum communication. The discovery reveals that light possesses more than energy and color. It has structure and orientation, a hidden choreography within its wavefront. Every beam, no matter how steady, carries a whisper of rotation, a reminder that even light's straightest path holds a graceful spiral within. Quantum entanglement can connect photons across vast distances. When two photons are created in a special quantum process, they can become entangled, meaning their properties remain linked no matter how far apart they travel. Measuring one instantly defines the other, as though a hidden thread connects them across space. Experiments have confirmed this strange behavior over great distances, proving that quantum information is not limited by classical boundaries. The phenomenon does not allow faster-than-light communication, but it forms the foundation of quantum encryption and teleportation. In a sense, entangled photons are partners in a cosmic dance, forever synchronized by their shared origin. They show that light's behavior cannot be fully described by location alone. It participates in a deeper, interconnected reality. Every pair of entangled photons reminds us that the universe is woven not only of matter and motion, but of relationships written in light. Information has been teleported between linked particles of light. Using quantum entanglement, scientists have managed to transmit the state of one photon to another at a distance, a process called quantum teleportation. No physical particle travels between the 2 points. Instead, the information describing the photon's properties is transferred through the shared entangled connection. This achievement demonstrates the possibility of future communication systems that rely on quantum states rather than electrical signals. Each experiment confirms that light can carry information not only across space, but across the abstract boundaries of quantum reality. The process is delicate, requiring extreme precision and near-perfect isolation from noise, but it has already been repeated many times in laboratories around the world. Teleportation of information through light points toward technologies once imagined only in fiction, where the very structure of reality becomes a communication channel. The future of information, it seems, is written in photons. The human eye is most sensitive to green light in daylight. Within the visible spectrum, human eyes respond most strongly to light near the middle of the range, corresponding to green. This sensitivity reflects the evolution of vision under the sun's emission profile, which peaks at similar wavelengths. During daylight, our cone cells dominate, providing color perception and sharp detail. They are tuned to detect small differences around the green region, where the balance of brightness and contrast is greatest. At night, rod cells take over, shifting sensitivity toward the blue and dimming our sense of color. The overlap between biological design and solar spectrum ensures that we see the world with optimal clarity in natural light. Artists and photographers exploit this by using greenish hues to convey brightness without glare. When you look across a sunlit field, you are witnessing a perfect partnership between star and species, vision tuned to its native star. Red light travels best through fog and dust. When light moves through fog, smoke, or dust, shorter wavelengths scatter more readily than longer ones. Blue and violet rays bounce off tiny particles, while red light passes through with greater ease. This is why warning lights and brake lamps are red, and why sunsets glow crimson when sunlight filters through thick air near the horizon. The same principle explains why distant stars sometimes appear reddish when viewed through interstellar dust. Scattering depends on the relationship between wavelength and particle size, making red the survivor in hazy conditions. In fog, red light remains visible long after other colors fade, guiding travelers safely. nature uses this effect as well. Deep-sea creatures often appear red because that color disappears first underwater, rendering them nearly invisible. In both air and sea, the behavior of light defines what can be seen and what remains hidden. Cloudy days create soft, diffused light all around us. On overcast days, sunlight loses its sharp shadows and becomes evenly distributed. Clouds act as vast diffusers, scattering light in countless directions. The result is gentle illumination that reveals color and texture without harsh contrast. Artists and photographers prize this quality for portraits and landscapes alike, as it softens edges and brings out subtle tones. In nature, diffuse light reduces stress on plants and animals by moderating extremes of brightness. The same principle guides architectural design, where translucent materials and reflective surfaces mimic the sky's soft glow. Though many people associate cloudy weather with gloom, the light itself is exceptionally kind. It reveals details hidden in direct sun and gives the world a muted calmness. Under such light, everything appears closer to its true color, neither dazzled by brilliance nor lost in shadow, but bathed in quiet balance. During an eclipse, the sun's halo of light becomes visible. When the moon passes directly in front of the sun, its disk hides the star's blinding face, allowing the faint outer atmosphere, the corona, to emerge. This halo of light extends far into space, shimmering in filaments and arcs shaped by magnetic fields. Normally invisible because of the sun's brilliance, the corona reveals itself only during a total eclipse or through special instruments called coronagraphs. Observers describe it as an ethereal crown, radiant yet ghostly. Scientists study its structure to understand how the sun's magnetic energy flows outward and drives solar wind. The fleeting moment of totality transforms day into twilight, and the hidden face of the sun becomes a delicate sculpture of plasma. The corona reminds us that even within overwhelming brightness, there are subtler lights waiting to be seen once the glare is gone. The combined glow of all galaxies forms a faint cosmic light. Beyond the stars, we can see lies a background glow made from the sum of every galaxy's light across the universe. This cosmic optical background is incredibly faint, drowned by the brightness of nearby stars and planets. Yet instruments in space have detected its presence. It represents the collective history of stellar creation, each photon a trace from a distant sun. The glow acts as a record of cosmic structure, helping astronomers estimate how many galaxies exist and how quickly they formed. It is the soft hum of starlight on the largest possible scale, the residual radiance of all the fires ever lit by gravity. When we gaze into darkness between constellations, we are not looking into emptiness, but into a subtle sea of ancient light, an intergalactic whisper of everything that has ever shone. Neutrinos are born beside photons in the hearts of stars. Deep within every star, nuclear fusion converts hydrogen into helium, releasing vast amounts of energy. Along with photons, another kind of particle emerges, the neutrino. These ghost-like particles interact so weakly with matter that they pass through entire planets without slowing. While light may take thousands of years to escape a star's interior, neutrinos leave almost instantly, carrying direct information about the nuclear reactions at the core. Detectors buried underground or under ice record the rare occasions when a neutrino collides with an atom, allowing scientists to glimpse the hidden workings of stars and supernova. In this way, light and neutrinos form two sides of stellar communication, one that illuminates the surface and one that whispers from within. Every beam of sunlight that warms the skin has an invisible companion, a stream of neutrinos silently passing through, unbroken and eternal. The universe once glowed before it became transparent to light. In its earliest moments, the universe was a dense, hot plasma where light could not travel freely. Photons continually scattered off charged particles, trapped in a fog of energy and matter. As expansion cooled the cosmos, atoms began to form, allowing light to move unhindered for the first time. That ancient radiation still fills space today as the cosmic microwave background, a faint echo of the universe's birth. It carries the imprint of temperature ripples that later grew into galaxies and stars. When scientists map this relic light, they are effectively seeing the oldest picture possible, the moment when darkness began to exist. The transition from opaque to transparent marked the universe's first dawn, when light and matter parted ways. Every photon from that era has been traveling ever since, a silent memory of creation written across the entire sky. Even empty space holds a whisper of ancient light. What seems like perfect darkness is never truly empty. Throughout the cosmos, a background glow persists, a remnant of the Big Bang itself. This light has stretched into long microwaves as the universe expanded, cooling from a blinding blaze to a near-freezing hum. Sensitive instruments can still detect it, finding the same faint signal in every direction. The presence of this cosmic microwave background confirms that all of space was once filled with radiant energy. Even between galaxies, where no stars shine, the universe still glows softly with this ancient warmth. It is a reminder that emptiness is not nothingness, but the quiet residue of everything that has ever been. When we look into deep space, the darkness we see is not absence but memory, the faint afterglow of a universe still carrying the echo of its first light. Every photon still traveling carries the memory of the universe it left behind. Each particle of light is a messenger from its origin. Whether born in the core of a star, released by a supernova, or scattered from a cloud of dust, a photon preserves information about where and when it began. Its wavelength, polarization, and direction encode details about temperature, motion, and composition. As it moves through the expanding cosmos, the photon stretches, reddens, and cools, yet it continues its endless journey. When it finally meets an eye, a telescope, or a grain of dust, the message is delivered. To observe the universe is to read these messages written across time. Every beam of starlight, every glow reflected from a planet, and every faint pulse from a distant galaxy carries within it the memory of its birthplace. Light is the storyteller of the cosmos, endlessly traveling, endlessly remembering. Light has been our companion from the very beginning. It shaped the stars, traced the edges of galaxies, and painted the first dawn across a world that was once only shadow. Every beam that touches your skin began its story long ago, crossing impossible distances to find its way here. It slips through leaves, glints across water, and folds itself into the rhythm of your heartbeat. It connects oceans, skies, and minds, carrying whispers of creation in every golden wave. Even the light around you now, soft and quiet in this moment, is ancient. Some of it was born in the heart of the sun, some in stars so far away that their light began its journey before there was language, before there were eyes to see. Yet it keeps arriving, endlessly, patiently. The same radiance that lights distant nebulae now glows gently through your window, threading your world to the greater universe beyond. Wherever it travels, light remembers. It records the fingerprints of every atom it touches, the stories of every star it leaves behind. It tells of beginnings that never truly ended, of energy that changes form but never fades. Even in the depths of darkness, light is never gone. It only rests, waiting to be seen again. As your thoughts drift towards sleep, imagine that same quiet radiance flowing through you. The warmth in your chest, the calm behind your eyes, the stillness that settles in your breathing, all are echoes of the same cosmic glow. You are not apart from the universe that shines. You are part of its light, briefly gathered here, then gently released again. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. For now, just breathe. Let your eyes grow heavy, and let the light of the cosmos cradle your mind. Quiet, infinite, and kind. Good night.